Okay, everybody, can you hear me? Well, I can hear myself anyway, so that's a good start. Welcome to the Saturday afternoon session of the AMSAT Colloquium 2023. Looking at the program, I can say it's going to be three very varied and different lectures. So to start with, can we welcome back John Hislop, who is going to talk about SPARKI.
Yes, welcome back. This is my second talk today. Yep. Hang on. Oh, right. Oh, sorry. Yeah. Second talk today. Yeah. You probably know me from Coding Week last month. Yeah. Any nods? Yeah, oh, yeah. Somebody. You did some coding that week. Excellent. Or the STEAMettes. They're a group of youngsters who are into science, technology, engineering, art and maths, and they're all girls. 2 years ago, they gave a virtual talk about having fun with amateur radio, electronics and coding. They're only about 9 and 10 years old. Okay, but I am passionate about education, outreach and training. You've probably downloaded my foundation manual from Apple Books, free. It's got about 50 activities in it for youngsters to engage them. It really annoys me when in the foundation manual it says you need to know the impedance of a cable needs to be 50 ohms. Don't worry what it means, just that really not. I'm a physicist, I want to know what it means, and I explain it in my manual. My foundation manual must be the only amateur radio manual with a picture of a fetus in it. Yeah, a fetus. Picture of Millie before she was born, because gel is applied to the stomach to match the impedance. Yeah. Right, yep. Okay, so next slide. I've written an intermediate manual for youngsters. Again, about 50 activities in it to engage them. Yeah, again, free. And I'm working on the full license for youngsters. Bit more difficult, but we're getting there. I'm halfway through, and when that's done, I will do a direct to full manual for youngsters, which will come out soon. Okay. So this is about the SPARKI project, SPARKI initiative. Yep, that's what it stands for, and it comes from ARISS USA. And the idea is of this kit is to promote amateur radio to schools and colleges to get them thinking about doing an ISS contact or just general education. Okay, it's all free. The manual you can download, and yeah, it's at the ARISS USA website. Just look under lesson plans, and the software also from Alan Johnston's GitHub. Right, so all free stuff. What's not free is the kit. So I will talk about the kit. It costs about $1,000. It's going out to 80 schools across the States. This is my opinion of it, not RSGB or AMSAT, all right, so I can say what I like. And at the end, I will present a budget version for the UK. $10, yeah. Right, so it was developed as part of this stereo initiative. Yeah. And this slide is taken from a YouTube video. Frank Bauer is to do with ARISS USA, and he's at some sort of fair demonstrating the kit. And it's a close-up. So you get the manual, you get the monitor, and so on. I'll give you the list in a minute. I think in the corner that's a bit of cake. Right. So what do you get for this kit? You get some slinkies and a snap circuits kit. Has anyone seen this thing? Yeah. It's pretty good. You just snap the components into place. Yeah, and you can make a Morse code generator. Ghost shriek machine. Yeah, Halloween coming up. Ideal. Yeah, it's great, but only the one. So if you've got a class of 30 kids, what are you supposed to do? Yeah. And you know, in the old days they had the springs and the connectors things, didn't they? Yeah, you're nodding, yeah, yeah. That's how you learnt electronics, yeah, yeah, yeah. So this is the latest version. I like this one. You can send your voice out on AM. Ooh, pretty cool. But if you look at the components, you just put the things together. Do you really understand what's going on? No, no. No. But yeah, it's pretty good though, isn't it? Yeah. So you get a Morse code key. Ooh, yeah, yeah. A tape measure. And a dongle. Right. Yes. Now, unfortunately, the FunCube dongle doesn't work on this software. So, strange. Rabbit ear antenna. Raspberry Pi 4. I expect they'll put 5s in now. And the SD card. Yeah. That's the secret for the whole thing. A little thing like that with ARISS Radio Pi on it, which you download and burn onto the SD card. They supply a keyboard, mouse, monitor, extension cable, and a book. Oh, where's the book? Oh, yeah. Right. This is in the kit. Ada Lace, and it's one of 6 books, and it's great. I've given it out to my STEAMettes and they enjoyed it. But what's a book that's for 8 to 10-year-olds doing in a SPARKI kit? Because as you can see, she's got headphones on, so she gets into amateur radio and speaks to an astronaut. Yeah, so that's why it's there. So it's called Take Me to Your Leader. So she gets these signals coming from space. Are they coming from aliens or no? It's coming from the space station. So that's why it's recommended. Okay, so I bought it. I thought it was great. Yeah, but there are some strange things about the kit. For the older pupils. Yeah. Okay. The aims of the kit are to promote amateur radio communications in general, understand what SDR is all about, and electronics, electromagnetic waves. So, yeah, pretty good aim, isn't it? And the best thing I think about it is the software and the book and the whole concept. Right? They're doing something to promote amateur radio. What are we doing? What are you doing? Ooh, oh. So there are some strange things in the manual. They recommend for the older students to read that book rather than the Ada Lace one for 8 to 10-year-olds. Has that got anything to do with amateur radio? Did he use radio to... Does anyone know? Right. He picked up signals on the radio, yeah. Okay. So an application of amateur radio. Right. Okay, thank you. Right. So this is my version, and there are three parts to what this promotion of amateur radio is about. The first one is, what is a radio wave? Now in the manual it says a radio wave is an electromagnetic wave. Full stop. That really annoys me. You can't say that and not explain what an electromagnetic wave is. Sorry. Yeah. So caused by, yeah. So next week, St. Peter's School in Broadstairs are speaking to the astronauts, and I use the SPARKI project to explain what is amateur radio, what are radio waves, and so on. So the first question you ask, these are the Space Club pupils who have been selected to ask the questions. So what waves are in this room now? Was the first question. Right, so they're surprised to think that they're sending out waves, heat waves. Yeah, obviously it's light and so on. They say sound waves. I say no, that's not electromagnetic. But there are radio waves in this room. We can pick up a local radio station, can't we? Yeah. So we got a transistor radio, portable radio, right, with the antenna. They'd never seen one before. What's that? They stream nowadays, don't they? Yeah, it's all mobile phone. Anyway, we showed that in this room there are a whole load of radio waves, and we can pick them all up. Okay, so how are waves produced? Start at the beginning. What causes a wave? An oscillation. The wind causes waves on the sea. All right. That young lady is Isabella. Yes, the renowned Isabella who spoke to Kjell Lindgren on the space station. She's in the Space Club, and she'll be putting out the call sign. She'll be going November Alpha 1 Sierra, yeah, from Golf Bravo 4 SPT, St. Peter's Thanet. She'll be calling them, and then we ask the questions. All right, you can do experiments with waves on the rope. That's a long wavelength, low frequency, and then you can't really see very well with the lights. Yeah, you need to turn the lights off so you can see. Yep, so you can see the high frequency waves in the corner there. The slinky is awesome. That's better. There you are. So again, you can show low frequency and high frequency waves. You can see the difference in the wavelengths, so to get an understanding of frequency measured in hertz. Yeah. Sound waves, right? Low frequency, high frequency. You need a signal generator and oscilloscope, of course, but they can hear the difference. Right, so we've explained that waves are caused by oscillations, right, of the loudspeaker or whatever. What causes radio waves? Now that's the difficulty. They're only 8 and 9 year old. Electrons, that's secondary school. So I did my best to explain what electrons are by charging a balloon and saying it's covered in electrons. You can't see them, but we know they're there because it can pick up bits of paper. Okay, so right, electrons. Right, to demonstrate the link between electricity and magnetism, I did a couple of experiments. You've got a coil there, the pupil there is pushing this strong magnet into the coil. At the moment there's no reading on the meter. Push it in and you get a reading. So a moving magnet will cause electrons to move. The nail is not magnetized, but if you pass current through the coil, it can pick up the paper clips. So a changing electron flow will produce magnetism. The two go together. Okay? Electricity and magnetism. Maxwell. Yes. Yeah. Now picking up the paper clips. So we understand what causes a wave. Well, I tell them it's caused by the oscillation of electrons. So in the antenna, the electrons are oscillating at 446 million times a second. Oh, what? So another child is in the other room. They are on the space station, and they take it in turn to ask the astronaut questions. So they're using radio. Yeah. So I did my best to explain what electromagnetic waves are, and they got to use them. And then you say, you're sending out electromagnetic waves. You're sending out heat waves, the oscillation of the atoms in your body. Yeah? Electromagnetic waves are entering your eye. Electricity and magnetism is going in your eye. It blew their mind. Yeah. So why not explain it? Why, instead of just saying radio is an electromagnetic wave, you know, it can be done. And they're only 8 and 9-year-olds. So I would keep, well, water waves, that's easy enough. Slinky, keep a slinky. If you're taking this SPARKI project to a school, they might have a signal generator and oscilloscope. They would have a tuning fork, I'm sure. The electromagnetic demonstrations, well, that's up to you. How strongly do you feel they should know about Maxwell's laws? Yeah. I feel very strongly they should. And PMR radios. So how much are we looking at there? Well, the school might have the equipment. You would have to provide the radios and buy a slinky. I wouldn't include longitudinal waves, which is in the manual. And I wouldn't talk about constructive and destructive interference. Kieran, you mentioned standing waves. It was in the book. Yeah. No, I wouldn't mention it. It's not necessary to understand radio communications. Would you say? Well, no, that's good. So now the second part. These children in the Space Club, they're going to be speaking to the astronaut. How does their voice get onto that radio wave up to the astronaut? Right, it's FM, isn't it? 145/800 is frequency for the astronaut. FM. What does that mean? Or we could use AM. What does it mean? Well, they understand frequency, they understand amplitude, but what does it sound like? Right? Digital signals. Right, machines use ASCII code. Right, so that's the next topic to explain. So to start off, what does our voice look like? So you're speaking into the microphone or loudspeaker there, and we got the waveform on the oscilloscope. So that's a sort of low sound from a boy. So we got a high sound from a girl, high frequency. Right. Poor thing. Now, I would include this in the software, GNU Radio. That program will demonstrate, right, FM, because it's got a VCO, voltage controlled oscillator, and they can hear what FM sounds like. You've got a carrier frequency, and it will change in frequency when you put another frequency onto it. So you've got yeah, so variable frequency 1K, and then you can change the frequency. Yeah, so FM, change in the frequency, and then you can show AM as well, the amplitude changing with the signal. Okay, they hear it, they understand it. It's all very well having that diagram in the book What does that mean? Yeah? You can hear it. Anyone familiar with GNU radio? GNU radio? Yeah? Yeah? It's good, isn't it? Yeah. Right. Morse code. Dida, yeah? Yeah. The kids love Morse code. Have you ever done any outreach work with schools or anything? Yeah. Yeah, they love it. That's Millie on the left there, star of the front cover of Radcom, and Natalie. They're not sending Morse code to each other, they're sending ASCII code. They're machines. Anyone here know their ASCII code? Oh, somebody said yes. Okay, so what is dida, 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 dida? I'll be very impressed if you know the answer. No? It's U. So ASCII code, you've got 8 characters for every letter. Oh, he's got to look it up. Right. Didad. Yeah? That's the only one I remember. All right. So, yeah, they're sending letters to each other as if they were machines. Right. Okay. Now, I did have 2 Morse keys. But you don't need Morse keys, do you? No, you can make your own switch. Yeah. Yeah. And you can use buzzers. Yeah, they've got a couple of buzzers there. But you could do LEDs with a class, sending light communication to each other. Very simple. So in Morse code, and maybe then ASCII code. ASCII code is in the manual, and I think that's cool. I think it's all right. Yeah. So I would include GNU radio, Morse code, obviously, binary code, and ASCII code. Right. I would also include the BBC microbit. Right. We had a little go beforehand. What are you shaking your head for? What? No. It's a board like that, a microcontroller, and it's got inputs. It's got a couple of buttons, A and B, and it's got a loudspeaker, radio, right? Yeah. So, yeah. On the front, it's got a yeah. It's got an LED screen, but this has been programmed to send Morse code by radio. So there's one for you. Right. You're the expert. Right. Do you know Morse? Okay, send them just one letter. So button A is a D, button B is a da. Put it to your ear, it's quite faint. Ooh. And again, do it again. It's not very... What letter is it? F. Oh. Yeah. Dardy, is it? Okay. Brilliant. Yeah. Yeah. You got the idea? 20 quid each. Yeah. So, yeah. BBC microbits, Morse texting. Yeah. Put it into the kit.
I just saw something very interesting which would probably appeal to youngsters to a certain extent, which is the table in a room, 2 tables in a room. There's 2 youngsters with mobile phones, one sat at one desk, one sat at the other desk. There's 2 radio ham operators skilled in CW, one sat at one desk, one sat at the other desk. When they sit down, the ones that are transmitting, sending the SMS message and sending the Morse code, pick up a thing and send it. And the Morse code is received quicker than the... And something like that, I think, is a good thing to see.
Yes, I like that idea, yes, comparing SMS with Morse code. Yeah. Yes, yeah. Okay. I wouldn't, in the manual it's got Ohm's law, You don't need to know Ohm's law to understand radio communications. And really, you've got to do Ohm's law. It's in my foundation manual. You actually do the experiment. You don't look at it in the book. You know, it's making a radio. Yeah, okay. From the Spark snap circuits kit, could do, but it's not necessary. And ciphers. Ciphers is in the manual, like Caesar's cipher. No, that's not amateur radio, is it? It's an interesting topic, but we don't need it. Right, finally then, radio in action. So we understand electromagnetic waves, we sense the Morse code, and FM, we've spoken. The different kinds of radio you can demonstrate. Local radio, you can pick up more signals from around the world. Hams talking to each other. FunCube, FT8, weather satellites. Listen to the astronauts next week, and SSTV images. All with this. This is the software. Amateur radio in space. It's awesome. It's brilliant, and it just put it on the Raspberry Pi. Connect up your dongle, connect an antenna, and you're away. Yeah. So, what can you do with it? Yeah. So listen to local radio station. Yeah. Pick up the waterfall. That's using cubic SDR, by the way. Yeah. It's got all the satellites up there. Yeah. Okay, so you can tune into Morse, listen to amateur radio stations, get the group, whoever it is, youngsters, whatever, to track the FunCube satellite. That's what they're doing there. Getting this FISA message. There's a message being beamed down to Earth, which they can, using the FunCube dashboard, they can get this message, as well as all the data about the battery and so on. So I would prepare them for real radio. They need to know their name in phonetic alphabet, a few Q codes, QTH, QSY, if they're going on to FM, and do a proper contact. So I'd keep, obviously, the software, do some real radio, transmit on 2 meters, and HF on 20 meters under supervision. I reckon I could give a talk with a support from an assistant in 60 minutes on what is radio, FM, AM, Morse code, and demonstrate picking up all these signals. Yeah, Morse code, hams talking, what have you, satellites. Yep, in 60 minutes. And no hitches. Right, so UK version, the Slinky, yeah, you can demonstrate a lot with that. A couple of PMRs, 446. Put GNU radio on the software. A school, if you're going to a school, they would have buzzers and wires, batteries. You need to take in LEDs. They still use incandescent bulbs. Yes, yes, horror. Yes, illegal. Yeah, I know. So you've got to take LEDs in, and a couple of BBC microbits. Now, primary schools are getting 30 microbits. Each primary school in the country that's registered, they're getting a class set. Get them to do Morse code. Use radio. Transmit to each other. How much is a dongle? How much is one of these? Anyone bought one recently? 20 quid. Yeah. Raspberry Pi 5. Okay. You do need a 4 at least, I'm afraid. Yeah. 50 quid, yeah. Say an antenna. I've not investigated this fully. You might just get away with a wire, a bit of wire strung out. Do you need a fancy rabbit is, or a mag loop, whatever. Maybe, maybe not. I need to investigate a bit further on that. But the book, yes. Don't forget the book, John. Yeah. So keep all that. £5. So this SPARKI project, I think, is fantastic. I think it's what we need. It can be interactive. Right? You saw the kids doing the experiments, didn't you? So if you're going to the Women's Institute, whatever, you say, right, come out the front here and waggle the slinky. Right, high frequency, low frequency. Yeah, for an hour. You do need an assistant. Right. But yeah, it can be done. UA3, another one there. Right. So it doesn't have to be for a school that's going to have an ISS contact. That's what it was designed for, because in the States they've got one every week. How many have we got this year? Just the one next week. Yeah. So it really is designed for ISS schools, but you can have any school. Take it to a school, after school club. Right, this is what amateur radio is all about. Okay, thank you. Any questions? They're stunned. Oh, yes?
Just following on what you said, your very first slide talking about Alan Johnson and the CubeSat sim, we have one downstairs. So if you want to come down and take a look at it.
Oh, brilliant. Okay. Yeah, so, yes.
Will it be possible to get copies of your slides, please? I couldn't get enough notes done.
Yes. And would you like the scripts? I've got the scripts for the presentations. Yeah. Yeah, okay. Yeah, it's on my memory stick, so yeah. Anybody else?
Yeah, I just wondered when the contact was next week.
Okay, yeah. Yes, the contact next week, so listen in on 145800 is Wednesday the 18th. Starts at 10:57 for 10 to 12 minutes. You'll hear Jasmine, the lady astronaut on the space station, answer their questions, but you won't hear the questions. You need to go to ARISS to get the questions published, aren't they? Yep. Or the web stream. Oh, right, okay, yeah. Live web stream. BST. BST, yeah. Yes, we're looking forward to Jasmine's answers to one of the questions. Do women make better astronauts than men? Ooh. There's fighting talk there. All right. Okay, any other questions? No? Yeah. Okay, thank you very much then. Yeah.
Okay. Thank you very much indeed, John. Are there any questions from the stream, guys? Okay, no questions from the stream.